This is John Lehman, and this project is for CSE 545 at the University of Louisville. This project will be exploring the set covering problem, a classic NP-complete optimization challenge, and we'll be looking at applying a genetic algorithm and wisdom of crowds solution and comparing it to some known benchmarks. So what is the set covering problem? The set covering problem asks us to select the smallest subset of sets that together cover every element in a given universe. We'll look at a simple example here in a second, which will make that a little bit more clear, I think. For a weighted SCP, which will be the main focus of our project, we're looking at the cost of each set instead of the number of sets. And because this is an NP hard problem, finding solutions to large data sets is often impractical, which makes it an ideal use case for heuristic methods like we'll be talking about today. Let's look at a simple SCP example. In this problem, we have 6 garden plots, 1 through 6, and we have 5 potential sprinkler installation options to cover those plots. Being an SCP problem, we want to cover all of our elements, which are garden plots, with the fewest number of sets, which are our sprinklers. So we're going to work through a greedy solution to this problem. We're going to start by selecting the sprinkler system, which is going to cover the most garden plots. So for us, it's going to be sprinkler B, and it's going to cover 2, 3, and 4. After we have selected that first sprinkler, we're going to eliminate the plots that it covered from our list. That'll help us select in the next set for our subsystem. Once we remove 2, 3, and 4 from our list of elements that we need to cover, we can see that there are 2 sprinkler systems now that cover 2 garden plots that we haven't covered yet. On this problem, we are agnostic as to which sets get included, so we'll just go with the first one and we'll add D along with B to our sets that we've selected. As you can tell from the image there, we only have 1 element which isn't covered, element 1, and there are 2 sprinkler systems which can cover that plot. So we will add set A, which then completes our universe and gives us a collection of 3 sets to solve this easy SCP problem. So there are a few takeaways here. There are multiple optimal solutions on even this easy problem. We don't particularly care which sets we include. I just kind of did it in alphabetical order. But within the context of the problem, possibly you want some plants to get more water than others. Some plants might be a higher priority in your garden, so you want them to have more coverage. So if you were solving this problem for an actual use case, you might move that redundancy where you needed it. The greedy heuristic doesn't guarantee an optimal solution. And if we wanted to make this a weighted SCP problem, it would be easy. We just add a cost to each sprinkler system and then look at the number of elements covered as a ratio of the cost of each system. The set covering problem has a lot of real-world applications, which is what attracted me to the problem for this project. Some examples are sensor and camera placement, any sort of autonomous system. How can you get the most possible data with the least amount of sensors? Scheduling, you can imagine if you have a machine shop and you have a certain number of machines and employees that can run various machines, but not every employee can run every machine. How do you create a schedule where on each shift you have at least 1 employee that can run every machine? Something like that. I think it's used a lot in airlines, scheduling flight crews, who has availability for each flight across a global network. Can also be used in healthcare, emergency services, where to place hospitals, how fire departments can cover different areas, network design, Wi-Fi deployment, large buildings, college campuses, airports, things like that, and is also applicable in feature selection for machine learning. I wanted to compare the set covering problem to the traveling salesperson problem that we've spent quite a bit of time with in this course. While both SCP and TSP are NP complete, they do differ. TSP is about finding the shortest route connecting nodes, while SCP is about covering requirements efficiently. TSP emphasizes sequence optimization, whereas SCP focuses on selection and coverage. So the differences would affect the algorithms that you would choose for each one. You can see that they do have different brute force complexities. The slide outlines the steps we'll be taking. First, we'll use a genetic algorithm to generate results, and then we will apply the wisdom of the crowds to aggregate those results. The data sets I use for this project are Beasley's benchmark SCP datasets from the OR library. These datasets do have known optimal solutions, which makes them good for comparison. Use varied sizes for the datasets, which should give me a balanced evaluation. The smallest dataset is SCP-41, which has 200 elements and 1,000 possible sets. And the largest is the NRG1, which has 1,000 elements and 10,000 possible sets. Parsing these was a little bit different than TSP files, but it is just text in a string that has to be parsed. For this step, we'll build an initial pool of random valid SCP solutions. Each solution is created by covering uncovered elements step by step with random sets until full coverage is achieved. We use a population size of 200, which we scaled back quite a bit from where I started, and we'll talk a little bit more about that later. So once we have a full population, we calculate the cost of each cover. We'll use a fitness bias selection, so the 10 lowest cost solutions are kept into the next generation and used as seeds to form the children for the next generation. And by doing this, we prevent the lowest cost from ever going up, since we're preserving the lowest cost from each generation. Crossover is our baby making process. It mimics biological reproduction by combining the genes from two parents to produce offspring. Within the context of the SCP, a gene is a set in a given solution. So we take two parents, and each set has a 50% chance of being inherited from the parent. This will create new combinations that might yield better results. And it's important to note that at this point, because we are removing and adding genes, that the solutions might not be SCP valid. We could either have incomplete solutions that don't cover all the elements, or we might have redundant genes, duplicates of sets, or just unnecessary sets at this point. Mutation introduces randomness to maintain genetic diversity and avoid premature convergence. So we use a swap mutation. Each child has a 20% chance to mutate. And if the child does mutate, we're going to randomly remove 5 sets and then replace with an equal number of random sets. And this randomness allows the surge to explore new regions of the solution space that the crossover might miss. After reproduction, some solutions may no longer be SCP valid, meaning that it doesn't cover all the elements. So we'll use a greedy heuristic to repair these. We will iteratively add the cheapest set that covers the most remaining uncovered elements. And this will ensure every offspring is feasible and near optimal. which is going to provide us a solid foundation for evolution. So for evolution, we will repeat that reproduction process over several generations. And over time, the best cost typically decreases or stabilizes, showing convergence towards the global optimum. For this project, I used 10 generations, which was close to get near optimal results for several of the data sets. And like I talked about a little bit earlier, I ended up scaling back the parameters quite a bit on this model compared to, say, the TSP. The graph on the right here is the results of the largest, the NRG dataset, and you can see that the curve is nearly flattening after only 10 evolutions or 10 iterations, which caused me to kind of scale back just so I could test the wisdom of the crowd's functionality a little bit better. The wisdom of crowd stage will aggregate the best genetic algorithm runs. We're going to run the genetic algorithm 5 separate times and then combine them all by weighting sets according to inverse cost and hopefully leverage the group intelligence. And so this ensemble approach smooths out randomness and should yield consistent near optimal solutions across runs. Let's take a look at the application and some of the visualizations. Okay, so we will select the smallest data set, SCP-41. And it'll take a few seconds here. It'll run through the process we just talked about, generating multiple generations, selecting the parents, and then coming up with the result. So, as we can see here in the GUI, we can go through each of the genetic algorithm results. We can see that the paths are going to vary a little bit usually. Excuse me, covers, not paths. We have total costs for each one. We can see the number of sets that were used in each one, the calculation time to come up with each solution, and then the wisdom of crowds aggregate. So let's look at the distribution of each set and kind of explain what's going on here. We have elements listed on the left, and then each set is listed across the bottom. And we're only displaying our solution, so we're not going to see sets that aren't being used. And by doing this, we can look across horizontal rows and find any redundancies. So for example, right here, it looks like set 1 is covering element 109, and set 2 is also covering 109. So if we were to look into each of these, we're going to see that set 1 and 2 are probably also each covering an element that isn't being covered by any other set, or else they would have been removed for being redundant. Another thing we can notice on this graph is that because sets are ordered in terms of their cost, the lower numbered sets have a lower cost. We're not going to have very many high numbered sets. So even though we have a total of 1,000 sets available, the highest set that we're actually using is 432. And the next highest after that is 274. And we're going to have a lot more down here in the sub 50 range because those are just the lower cost sets. Then we can go look through each of the genetic algorithm and look at the generation graph for each one. And as we can see, we're starting to level off very early, which is why we kind of limit it to only 10 generations and smaller population sizes, because just the genetic algorithm combined with the greedy heuristic, it's already given us very strong solutions on its own. Next slides show quantitative results for several benchmarks. For the smaller and moderate problems, the genetic algorithm consistently achieved or closely matched the optimal known cost. You can see we did 5 runs with 5 genetic algorithm runs each. We have an average And then next to that, we have the wisdom of the crowds result. The wisdom of the crowds result were slightly higher, but did seem stable across all runs. Here's the next set of data, the SCP-61 and D1. This is notably the only run in which the WOC actually produced an improvement over the average GA. You can see on SCP-61 there. And it did actually find the optimal result, 138. But again, just very consistent results across these data sets. These are the two largest data sets. On NRE here, we can see that the genetic algorithm actually found the optimal results, all 25 iterations that we did, which of course caused the wisdom of crowds to follow suit and hit the optimal result several times. The NRG is the largest data set, and I think we're starting to see some of the widest variance of the wisdom of the crowds on that data set. So summarizing those results, the experiments confirm that the genetic algorithm with the greedy heuristic repair is a very strong solution for set covering. So much so that I think the wisdom of the crowd struggled to really be able to improve upon it. But the wisdom of the crowd does add robustness, and it can help reduce variability. So looking at these small and moderate instances, the GA was within a few units of optimal. The WOC had slightly higher cost but was stable. For the large and more dense instances, the GA and WOC for the first two, the D1 and the NRE, were near optimal for both of those. And the NRG, as I mentioned before, it was one of the ones where we saw the most variance between the WOC and the GA. So the key takeaway from this project, I think, is that even with limited tuning, the system produced near optimal results for complex data sets. The WOC approach adds resilience with minimal overhead. The runtime I have there at the bottom is the total runtime for the whole system, which includes the 5 GA runs, and that 0.8 milliseconds is the time for the WOC. So there's very little compute involved with the WOC, and it does provide that extra robustness over just a singular GA approach. So I think there is some promise for ensemble evolutionary strategies and large-scale combinatorial optimization. And finally, here are the references in this presentation. Karp's work on the MP completeness and Beasley's OR library dataset models.